Today we are going to finish the nonlinear solution methods with the ArcLength method. Then we are going to move on to the first part of geometrical nonlinearities, and today we are going to talk about kinematics, statics, and balance laws, the strong and weak forms. We'll start with the ArcLength method. Previously, in the case of force loading beyond the limit point of the equilibrium path, we have a convergence issue. Right? This is because the line of force loading does not intersect with the equilibrium path. And once the Newton iteration goes towards or beyond the limit point, it diverges. Mathematically, this is because the tangent stiffness matrix, geometrically represented by the tangent of this equilibrium path, becomes zero. So when we calculate the tangent, if we have a point with a flat gradient, then k here is zero. And when we calculate the correction to the incremental solution, then this term becomes undefined, and our solver cannot find convergence. So afterwards, I'm going to show you how the ArcLength method is able to overcome this limitation of the Newton-Raphson method. And the trick is to introduce the loading parameter lambda, or the external force loading F external, as an additional unknown. Previously, we introduced the loading parameter as a parameter, right? So this is some user-controlled input to the system equation. Now, we consider it as an unknown. Then you may ask, then what is known? What do we control as loading? And there we impose additional constraint. So if we don't impose additional constraint, we have one equation, which is the equation with residue, with two unknowns, and we can't possibly solve this equation. So we impose this additional constraint both as having a control, physically speaking, having a user control over loading, and mathematically speaking, to complete the system equation so that it's solvable. Now we have two equations with two unknowns. All right, if you look at this equation, it has, if we consider only scalar terms, it has delta A square plus beta here is a scaling parameter. Let's ignore it for the moment. And then this is basically the delta F external, so the incremental external force square, minus delta L square, and when we impose a constraint, we set it equals to 0. So this set of equations is what the solver would try to minimize eventually towards 0. So if you look at the form of this equation, it looks like an equation for a circle, all right? So if we look at the equation for a circle, we have x squared plus y squared minus r squared equals to 0. Okay, now this form resembles the form of our constraint equation. We have delta A squared plus delta F external squared minus delta L squared equals to 0. Basically, if we were to plot this set of equations, the constraint equation, on the graph where x-axis is A and y-axis is the F external, then the constraint equation would be the circle with a radius of delta A. Okay, so it means that this time when we want to apply the external force loading, the only parameter that we are going to specify is delta L. And we are neither applying a displacement loading nor applying a force loading, but we are applying a loading in the form of a circle, which means that the delta A and delta F external could be of arbitrary combination as long as their combination falls on the circle with the radius of delta A from the last equilibrium position, AT0. So the true equilibrium solution would be the intersection of this circle with our equilibrium path. So this would be our first incremental solution, and from this solution we can further draw another circle as our loading. I would call it a loading envelope, and then the intersection of this loading envelope with our equilibrium path defines the next equilibrium position. And this goes on, and when we reach closer to the limit point, we can still define this loading envelope, which is in the form of a circle, and it still intersects with the equilibrium path. So Unlike the case where we have the force loading, which once it goes beyond the limit point, it does not intersect with the equilibrium path. In this case, we have a closed circle, if you draw it fully, and it always intersects with the equilibrium path. So we have no problem defining the point of equilibrium in this case. And this can continue, and we go beyond the limit point. All right. This is a geometrical sketch of this constraint equation, and mathematically, this means that we have a well-defined tangent stiffness matrix even at the location of a limit point. Why? This is because now we have two sort of residues. One is our Euler residue, where it equals to f external minus f internal. The other one is our constraint equation, which we also try to minimize to 0, and two unknown variables, lambda and a. So we can define a so-called augmented tangent stiffness, which has the first term as our Euler tangent stiffness matrix from Newton-Raphson, as well as the other three terms. Right? We have the partial of r with respect to the new unknown, the loading parameter lambda, and then similarly we have our constraint with respect the partial of constraint equation with respect to our displacement solution A, and the constraint equation's gradient with respect to our lambda. So then we have an augmented tangent stiffness matrix with 4 entries. At the point of limit load, Ki becomes 0, but the others are not. So even when we reach the limit point, this augmented stiffness matrix does not become singular, which means that we can sort of invert it, and this correction term here is well defined. And then we can calculate the correction, we can add it to the previous incremental solution, and then we get the new incremental solution until convergence, means that until both r and g become 0. So to summarize, our loading increment becomes an additional unknown, and to make the system of equation complete, we impose an additional constraint equation, which in this case in the form of an equation for a circle, and then we obtain an augmented tangent stiffness matrix, which does not become singular at the limit point. All right, this is the mathematical background for the ArcLength method, and this is this augmented tangent stiffness matrix is the key towards solution. So it does not become singular, then it's solvable, it's invertible, and then we can gradually increment our solution until convergence. Previously, this was not achievable with Newton-Raphson once the key I becomes 0. This is the key aspect, and let us do the same thing as before and try to draw the iteration plot for a single increment, and we focus on this particular increment where we had difficulties with Newton-Raphson. Here we have a limit point. Now instead of writing a straight line as before, which corresponds to the case of force loading beyond the limit point, now our loading is a sphere. We have a loading envelope with a radius of delta L, and our objective here is to find the intersection as our equilibrium solution. And you can see that this intersection exists and is very well defined. So we can form a first estimate, delta A1. Then we can form our first residue R1. And then if we enforce the constraint, we can see that there's a very well-defined direction where the residue would gradually reduce to 0. So if we move our estimate solution along this constraint circle, the gradient, the augmented tangent stiffness, would gradually through iteration move our point towards reducing residue. And this is the direction, and eventually you can see that if we follow this direction, we will come to this point, which is our solution point. All right, and this is the direction along the equilibrium path where we would have a reducing g. G is only 0 along the circle, so at this point g is non-zero. But if we move towards that direction, which is the direction of the gradient of this equilibrium path, we would gradually find our way there. So basically, this augmented tangent stiffness would have contributions of both these tangents, right, to try to help us to find our way towards the intersection. Okay. So of course, in this augmented system, the gradient has 4 contributions. So it has 4 entries. So it's not correct to draw the line of gradient as exactly the gradient of only the equilibrium path. But the story is the same, is that as long as the tangent stiffness matrix does not become singular, then we have a very well-defined system equations to solve, and through iterations, we can gradually find our way towards reducing both the R and G which corresponds to this point where both of them become 0. So this is the mathematical foundation as well as the geometrical sketch of the ArcLength method. In practice, different constraint equations exist, but the spherical ArcLength is the most standard or most well-established method. We've only mentioned about the difficulty of Newton-Raphson in the case of force loading beyond limit point. Previously, we also covered a case with the displacement loading and in the case of snap back. So there, the difficulty was that with displacement loading, we cannot capture this part of the curve. This is because as we gradually increase the displacement, once it goes beyond this turning point, we can't possibly find an intersection with this part of the curve. So it misses this part completely. This difficulty can be overcome by the ArcLength method because we can always find the intersection between a closed circle and whatever curve you have. So unlike in the case where the straight line doesn't intersect with this part of the curve which is snapping back, a closed circle always intersects with it. So this point is well defined, and we have our augmented tangent stiffness. Through iteration, we can always find our way there. So you can see that if we have a point here at the point of limit snap back point, our augmented tangent stiffness matrix will move our estimated solution towards a direction of reducing residue, and gradually we will find our way there. This is the way, the reason why ArcLength method is able to overcome the limitations of Newton-Raphson in the case of both snap through or limit point and snap back behaviors. And in practice, we can vary this parameter delta L. So in the case we have a very smooth curve, we can simply use a larger delta L. While in the case we have a smaller curvature, then we need to use a smaller delta L to properly capture this part of the curve. Otherwise, imagine we have a very large radius, then the next intersection could easily be already this point. So where we imagine this line extending, and you jump from this point directly to this point, and then you miss entirely this part of the curve. During the classroom session, one interesting relevant question was raised, and the question was that what if you have two intersections here, what if it goes backwards? The way to detect whether we are going backward is quite simple. So we came from here to here, so there is a sort of a vector defined. And now if your solution is going backwards, then the dot product between this vector and this vector is negative. Then you know that you are going backwards, and you need to pick the direction where the dot product between your new estimate direction and your direction of loading from the previous increment is positive. Then you know that you are not going backwards. Another question that was raised during the classroom session was that what's the computational cost when compared to standard Newton-Raphson? And the answer is that it's more costly because we have an augmented system. We have additional unknowns, which is lambda, the loading. So we have a larger system to be solved, and so the recommendation is to always use full or standard Newton-Raphson first. And then if you run into a problem, then you switch to ArcLength method. And you can't use both methods at the same time because they are addressing at different system equations with different unknowns, right? So you have to use one at a time. And yes, this is everything that I would like to cover on ArcLength method.